I just hit the recording button, so I'm going to go ahead and record this series. So for those of you who want a copy of it, please email me at the end of the program here, and I'll get you a link to the video, so that way you can either rewatch it or share it with any of your colleagues or coworkers who weren't able to make it this morning. Also, too, I have Jai Musselman, who is also on the call. He'll be monitoring the question and answer box. So throughout this presentation, if you have any questions, just go ahead and type them in there, and Jai will quickly answer them. But we'll also leave some time open at the end of this to type questions in as well. So Jai is our business development manager out of Florida. So he's been with the company a long time. So he's the best person to answer a lot of the questions. But with that, we'll go ahead and get started. So first, to kind of get us going here, here's going to be our quick agenda as we talk about engineering the low voltage lighting system. And start off as I'll introduce myself. I'm Brian Qualls. I'm the National Business Development Manager for Unique Lighting Systems. I've been with the company now coming up on 9 years. So prior to that, I was actually a landscape architect. And in fact, I still am a landscape architect. I still carry my licenses here in Arizona. And as my experience goes, I've pretty much worked for just about every type of landscape firm out there, from a small little firm all the way up to um, a big engineering company. In fact, I ran the landscape architecture department for AECom here in Phoenix for a number of years, and then 9 years ago came over to Unique Lighting. The reason why I bring this up is just kind of let you know that my perspective is a little different when teaching these classes. I definitely come from the drafting table side of the business. I do have some field experience as well, so I kind of have a good, well-rounded approach when training and looking at low voltage lighting. So what is low voltage lighting? So ideally what we're going to be talking about is that the systems are based on 12 volts versus 120 volts. The idea behind why I bring this up is it gives us a lot more flexibility in the field. A lot more people can handle a low voltage system as compared to 120 volt. The systems are allowed to be buried only 6 inches deep. We don't have to put the wire and conduit. You don't have to go and get your apprenticeship and become an electrical contractor to install it. Just about any landscape contractor can install it. The landscape architect can design it. So we got a lot more flexibility um, on the low voltage systems than we do the line voltage. In addition to that, with the kind of advancement of LED into our end a lot more today before, when we just had just the restrictions of voltage drop and amp load isn't as great as it used to be, and then we can just do a whole lot more from there. So as we go through the first things we get started, we're going to have to talk about kind of getting some definitions. I hear this a lot, where a lot of the phrases and wording kind of change when talking about low voltage lighting systems, and each of them truly have their own, and I want to make sure that we understand each one before we go through. So first off, the National Electric Code. So even though we call this landscape lighting or low voltage lighting, it's still electricity, and it's still there's still a section in the National Electric Code that pertains to low voltage lighting. And really what it states is that anything that operates at 30 volts or less is considered low voltage. A lot of people don't quite understand that, and they think that low voltage is a 12 to 15 volt kind of range, when actuality you can go up to 30 volts. So there's several manufacturers, and us included, that have transformers that will go all the way up to 24 volts, and there used to be a 24 volt system. And the reason why that was still allowed was because it followed the National Electric Code of being under 30 volts or less. So there are transformers. We've got going to be some new little transformers launching here at the end of the week. They're going to have higher taps, so that way you can get those longer reaches and longer runs to account for voltage drop. And yes, voltage drop is still a thing with LED, and we'll talk about that as we run through. So to kind of get us all on the same page here, one thing I like to kind of talk about is just about everyone that I talk to, everyone I work with, they've got some sort of experience in irrigation, whether they've installed it or maintained it or have it at their house or what have you. So when we're talking in irrigation, the big things that make an irrigation operated heads. You've got the fittings, which are your elbows and your T's, your point of connection, so that's where water's coming out of the house or out of the building, and then the controller that's hung on the wall somewhere that can actually turn the zones on, turn the valves on and off when needed. So with lighting, that translates over to our fixtures, or same thing as our spray heads. Our wire acts as our pipe. Our hubs are our fittings, so the elbows and T's and things. And we'll talk about that in this presentation as well. Our point of connection is the primary power, so a place where we can plug a transformer in at 120 volts. And then our transformer does dual job. It's double duty kind of operation there, where it not only takes the power from 120 volts down to 12, but also too, we're using it as a controller. Oftentimes people will call me and call it a controller, when actually there's just additional hardware that are attached to the transformer to control it, but still it does double duty for us on the low voltage lighting side. So the big three items, the big thing definitions that are out there that a lot of people get confused are watts, amps, and volts. Now they're all very different. We're going to go through each one, but now with LEDs, there's kind of a fourth definition we need to talk about, and those are volt amps. And so I'm going to talk about volt amps last, but let's kind of quickly go through what each is. So a watt, that's your measure of your electrical power. So that's what we actually pay. Our electrical bill is based off of what there are watts. So if you open up your bill for last month, it'll say kilowatt hours. And so that's where so the more watts you have, the brighter the bulb and the more energy that you're using. Amps, that's the measure of the electrical current that's running through the wire running through the transformer. We're going to talk about how to figure out amps, but basically the amps is kind of, again, it's the electrical current as we run through. And then the volt, that's the electrical pressure. So the more volts you have, back in the halogen days, that was the brighter the bulb that we had, as you go through. And then if you had less volts, it would be dimmer. So same thing, just like an irrigation system or sprinkler system, the more pressure you have, the more water that's pumping out, the less pressure, whether the sprinkler head will even open or water will just kind of fiddle out at the end. And then a volt amp is basically the measure of the apparent power. So volt amp is another way, or a fancy way of calling it, a power factor. Everything we use, everything we plug into a wall or what we do has a power factor. Even back when we were doing incandescent and halogen days, there was a power factor included, but that power factor was a measure of one. So no matter what number you have and multiply it by one, you get the same number that comes through. Well, now with LEDs, because now that we're using electronics to actually produce the light, the power factor has gone up to about 1.5. And what's interesting about that is, even though the power factor is 1.5, at the end of the day, we're still paying the power company what our watts are, but what the apparent power, what the transformer sees and what the wire sees is that volt amp, is that 1.5 times power factor from the wattage. Now, most manufacturers, including Unique Lighting Systems, will publish what our volt amps are. It's on our spec sheets, it's on the boxes. And as you can see, so here's our PAR 36 5 watt that actually pumps out 6.7 volt amps on the other side. So this is, if you're adding up all your watts to figure out what transformer you need, this is the number you need to be sizing your wire and need to be sizing your transformer for, not that. Now, it's not a huge jump, but you can imagine over time, if you're adding 10, 15, 20, 30 lights, this will add up and you could be potentially limiting a transformer or almost overloading a transformer if you're using the wrong number. Now, if you're using a manufacturer that doesn't publish what their volt amps are, then go ahead and multiply their watts by 1.5. It'll get you close enough. It'll get you pretty dang close of where you need to be measured by the volt amps and not so much the watts. So let's kind of put this back in perspective. So, the three things we've got to look out for in irrigation is our gallons per minute. So how much water are we using? The pressure in the pipe. So we need to make sure we've got enough pressure or the correct operating pressure. Because if we have too much, as I mentioned before, we're going to be missing the water coming out of the sprinkler heads. And if I don't have enough pressure, then the sprinkler head may not even open, or if it does, the water is just kind of piddling out. And then the big thing is we need to watch out for the velocity or feet per second inside that pipe. You look at any manufacturer, Toro's book will tell you how many feet per second you get at certain pressures at certain size pipe for PVC or Schedule 40 or what have you. So we do the same thing in low voltage lighting. So our watts or our volt amps are the same thing as our gallons per minute. The pressure in the irrigation is the same thing as our volts. And then I'm accounting the velocity as, or your feet per second, as amps. So every piece of wire that's out there has an amp rating. And if you exceed that amp rating at any point in time or over time, you'll actually start to melt the wire, melt the jacket, and then that's where we start getting problems later down the road if a wire has too many amps on it. Or same thing with a pipe. If there's water's running too fast through that pipe, it'll eventually erode the pipe and cause a break. Same thing here will cause a break in the wire. So how do we figure out what the amps are in a transformer or in the wire? And the big thing is we use Ohm's law. So Ohm's law is super, super simple. And basically all you're doing is you're going to take your total watts divided by your volts, and that'll give you the amps. So the best way you can figure that out is to do, your pre-planning. So if you're laying something out on a plan, or if you're about ready to buy a bunch of fixtures to put in at a location and design it in the field, this will help you kind of add up all those watts. Hey, I'm going to put this on the 12 volt. It'll then tell you what your amps are. All manufacturers who make wire will have an amp max rating on the wire. So then hey, if I need to, I want to keep myself at 16 amps on 12 gauge wire, I can go ahead and do the math real quick, and maybe I need to limit my runs, or maybe I need to split them up or get bigger wire. The other side of that too, which is really nice on the construction side, is it gives you the ability to double check your install. So if you go out there and install a bunch of fixtures on a wire run, and you plug it in your transformer, you pull your amp probe out, and you do the math and say, okay, I've got 15 fixtures, and this is where I'm at. I should be pulling about 7 amps. You put your amp probe on that run, and you're getting a lot less or a lot more than what you figured in the math, then you've got an issue, right? So usually if you're saying, hey, I should have only about 5 or 6 amps, you do an amp check, amp probe, and you're pulling 9 or 10, then hey, maybe I've got a short somewhere. I've got a wire that's not connected correctly. Or if it's way low, then maybe I don't have a fixture plugged in right or whatever. So it's a really nice way and quick and easy way. Everyone's got a calculator on their phone these days, just to double check once your install's in there compared to what your amp probe's telling you that you've got what you planned for during your installation. So quickly, you can see how it works. So if I've got 240 watts on one run and I've got it on the 12 volt tap, I should have 20 amps. If I go out there and then double check it with my voltmeter and find out that I've got 10 amps, well, then maybe half these lights aren't working, or they're not, half of them aren't on. If it's above the 20 amps, then I've got a short or I've got a problem somewhere. So as you can see, as we're working through this, as we go up in volts, our amps go down. And that's just a product of the math. So when you kind of look at that, it kind of starts to make sense. Well, geez, all these power plants are powering my homes, or you know, hundreds of miles away from where I live, or maybe not hundreds, but it's miles and miles of miles away from where I live. How are they getting power to my house without having to do with voltage drop? Well, if they're doing 1.21 gigawatts, their voltage drop is virtually non-existent because their voltage is so high. So as we go down in voltage, that's how our amps just go way up, and that's when we got to start using bigger wire on our systems. So out of all the things that we're working with Ohm's law, the most important aspect, the one thing that we really need to be concentrating with, is amps. That is the one that is ultimately where we're at. If you were to call me, if you've got a system installed and something's not working right, or you can tell that something's not going on, the first thing I'm going to ask you is, what's your amp load on the transformer? What's your amp load on the wire? To make sure we're not overloading anything, because that's usually where the number one problem is. And most of the time it's a short somewhere, And in order for me to find that short is I got to figure out what the amp load is. So it's very, very important for you, people that are contractors, installers out there, is to make sure you've got an amp probe. There's no other way to tell what's going on. You can't touch and feel the wire. You can't, understand, hey, what's going on with the system. Everything's invisible, so the amp probe tells you where you're at. There's a lot of really, really good irrigation techs out there that I've worked with that, can look at a system, an irrigation system, and just tell whether the pressure's off. I've seen guys taking the a screwdriver up to their temple and put it onto a valve, and they're really good at that. And unfortunately, we can't do any of that without some sort of amp probe on the lighting side. And if you don't have one, I will highly recommend getting one, and then figure out how to use it to make sure you get the right amps and your right volts at your system as we're going through. So next, we're going to talk here about voltage drop, and we're going to spend more time on it probably than you expect, because what's happening right now is um, a lot of people are now kind of assuming that, well, it's LED, voltage drop no longer exists, or I don't have to worry about voltage drop anymore because the LEDs are going to regulate the voltage. That's really kind of a half true. What I tell everyone that's out there is nothing's changed with LED other than the fact that our loads have greatly decreased. So a watt is still a watt, an amp is still an amp, and a volt is still a volt. We're just using a lot less of them. And when LEDs first came out, we weren't quite sure how to use them. We weren't quite sure, you know, whether we could trust the readings we were getting, because it was new, it was new technology. So a lot of the people I worked with for years, they were still putting LEDs on 10 gauge wire. We were still doing the old halogen kind of philosophies, but just adding LED with it. And I can tell you with 10 gauge wire and LED, you've got to put a lot of LEDs on there to see any type of voltage drop. I mean, it was really, really low, but it was still there, but it was really low. And what I'm seeing now is that now that we're getting a better understanding and we're more used to LEDs, a lot of designers, a lot of contractors are now starting to use, you know, 14 gauge, even 16 gauge wire because of the fact that we're using less voltage. But now what's happening is the resistance and the capacity of these wires is also reduced. So we're falling right back into the halogen trap because if we're using smaller wire, that voltage drop is right back where it was because of the capacity of these smaller wires. Now, the other misnomer about how LEDs regulate the voltage really isn't true. What's happened is LEDs, their voltage range is a lot bigger than what it used to be in halogen. So the halogen, we had a small window, about 10 and a half to 12. Now with LEDs, it's 10 to 15. And what's great about the LEDs is that at 10 volts, I get the same light output as I do at 15 volts. So I just have a bigger target to order to let that LED operate, not so much having that the LED is going, oh, I'm only getting 10, I need 12, and it's regulating the voltage. That's not happening. It's just that our targets have gotten much bigger. We need to understand that to make sure you're still getting a minimum of 10 volts at your LED. Because if you get down to 9, the LED is not going to be able to increase that to make it work, and it will start to dim below that 10 volt system. So basically, as we talked here, voltage drop is just that decrease in voltage, and kind of put in perspective, going back to my beautiful diagram here of a water spigot. So if I had a piece of PVC pipe and I turn this water on and I got water coming out the end here, I'm going to have a constant pressure, and this pressure is going to, kind of run through this pipe. But if I were to start popping holes in the top of this pipe, you'll see that I'm going to have a lot more pressure towards the closer to the source and a lot less at the end of the source. And then depending on what size holes these are, it will also affect how much water is coming out the end of the pipe at this end. Same thing happens on low voltage lighting. So if you imagine this is your home run wire, and these are the lights that you're plugging into that system, the first one's going to receive, all the voltage, and the last one's going to receive the minimum amount of voltage. Now, again, it's not as big of a deal with LEDs as long as this is not above 15 and this is not below 10. Then everything will be, copacetic with that. But again, as we start using smaller and smaller wire, we'll start to see greater voltage drop, as if same thing if this was a smaller pipe. I would see greater pressure drop as if it was bigger. So again, as I kind of labored over this, why do we care so much about the voltage drop? Is because of the fact that we need to make sure we still have to hit that target. Now, for me, LEDs have just been absolutely awesome, especially on the older systems that weren't designed all that great, that had that dimming across the line. I could easily retrofit drop-in LEDs, make the system operate so much more without having to rewire the system, without having to dig anything up out of the ground. But when I'm doing a brand new install, I want to be as close to 12 volts as I possibly can, because that is the optimal operating range for an LED, is right at the 12 volts. And if you go below 10, you'll start to get those dim lights, and especially if you go above 15, um, you'll get no warning. They will fry. They won't handle 15 and a half. They won't handle 16. You go above 15, and I've seen it happen. I've seen guys, burn up 30 LEDs in one shot. That you go above that 15 volts. So I want to stay at 12. I want to give myself a little wiggle room, more up than I do down, because if I go down, I'm not going to kill the LED. But I want to be as close to 12 volts as I possibly can. So here's an example of what I was talking about, as far as this is an old halogen picture. I don't even remember where I got this picture. I don't even know where it is, but I can tell you with great certainty that the transformer is somewhere over here. They ran one wire all the way down, and you can just see how this is dimming all the way across the line. So LEDs would fix this for sure. As long as I wasn't above 15 here and below 10 there. If I were to just change all these halogens out and put LEDs in, I'd have a nice even light across the whole scene here and make it look, 10 times better than it does now. So how do we compensate for voltage drop? We kind of touched a little bit about that all the way through. So the number one thing is we need to understand that voltage drop still does exist, and just make sure that we know that it's there. But really, it's bullets right here on the screen. We want to make sure we've got the right size transformer. As we keep rolling through this, we are uh, seeing more and more transformers that will have a single tap. They'll only have a 15-volt tap, or they only have a 14-volt tap, or whatever it is. Um, you want to make sure you've got one that's got multiple taps, especially for the bigger jobs. The smaller jobs you're okay where you're both the bigger jobs, because if I've got longer distances and different circuit lengths, I need to make sure I've got the right size transformer, it's got the right size lugs inside of it. Of course, the correct, wire sizing and layout. You know, the most important piece of any lighting system is the wire, and it's the least expensive part of any wiring system, and it's the first thing, for whatever reason, everybody wants to try and save money on. Make sure you're doing it. I can tell you that I don't design anything below 12 gauge. I just don't do it. To me, it's just, this is lighting is so easy to expand. Low voltage lighting especially. It's such a great piece to put in your landscapes that I don't want to handcuff myself from the beginning. So I'll pay for it, and it's not the cost difference between 14 gauge and 12 gauge isn't enough to really make or break the bank on a project. So, but make sure you're using the correct wire size. So again, you don't handcuff yourself later down the road. Oftentimes I'll have to limit the circuit length. And what that means is if I'm trying to run a really long run and I've got 240 watts on there and I've got too much voltage drop, I'll cut that in half and run a second line back out from the transformer. That way, I'm not having to try and do any kind of, mumbo jumbo to try and make that work. Just cut that circuit length, add another line, and then you're good to go and make that work. So when I'm doing these classes, and even just throughout the week, throughout my kind of normal operating day, I get these questions all the time. I'll get a phone call, hey, what size transformer do I need? Or hey, do I need one transformer? Do I need multiple? And what's the biggest one is, what's the longest wire run I can have? So in order to do that, we need to kind of understand how a transformer works. So the biggest thing that I tell, the simplest, is you need to picture a transformer like a big bucket of watts. All right, so I've got a bucket of 300 watts. So imagine if I came, to your house and said, "Hey, I've got 3 glasses. What size pitcher do I need to fill these glasses?" Well, you can't answer that question because you don't know what size glasses I have. Are they little shot glasses? Are they big beer mugs? What am I filling with? And that's kind of what happens when I get that phone call is what size transformer do I need? I'm putting in 10 lights. Okay, what type of lights are you putting in? Are they 4 watts? Are they 2 watts? Are they 10 watts? Because that's going to affect the size of what size pitcher I'm going to need to fill those. So again, I'm looking at is I've got these glasses. Is 300 of my bucket going to be able to fill those glasses? Not until I know that, hey, each of these glasses are going to hold 50 watts, then at that point I know, yeah, you know what, there's 150, I'll have 150 left over. But before we do that, we need to understand that the National Electric Code states that a transformer can only be loaded to 80% of its capacity. So I can't use 100% that transformer. I got to make sure I got 20% of kind of extra left over. So instead of 300 watts, actually I have 240 because of the 80% capacity rule. But I'm still only pulling 150. So yes, that 300-watt transformer is going to be the perfect size because then I'll have 90 watts left over based on how that is all played out. Now, that's a lot to try and figure out, especially if you're trying to do this on the fly. If you're doing on a plan and you're trying to figure out what size transformer to give your MEP guy so he can size the circuit you're going to plug your transformer in, or if you're a contractor at the counter trying to figure out, hey, I'm buying all these lights, I need to figure out what transformer I need. The 80-20 rule is kind of what I use all the time. So basically, the best way to do this is take all the fixtures that you have that's out there and add 20% to that. So if I've got, 100 watts that I add up that I'm going to be putting into a project, add 20% to that. So pretend you have 120 watts. Then okay, now that's 120. Can I use a 150-watt transformer? No, I got to reduce that transformer by 20%. I'm only going to use 80% of that transformer, and then that way I can then understand maybe I need to bump up to a. Now, after you're getting out there and you kind of start doing the math, you can actually sit down and figure out what your transformer calcs are, get you a lot closer. But again, on the fly, use that 80-20 rule to make sure you're getting the right size transformer. So the next question I get is, what is the longest wire run that I can have? Now, again, you can figure out what that is, and I can show you how to do the math. But again, when you're on the fly, this is a great rule of thumb to use. So again, as I mentioned, I always like to stick with 12 gauge wire. So I'm going to assume that I've got 40 watts, so 10 4-watt LEDs. And that's what I'm going to use as my kind of sample project here. So those 40, so those 40 watts will drop roughly 1 volt in every 100 feet of line, right? So 40 watts 100 feet away will drop 1 volt in that distance. So knowing that my LED's minimum operating range is 10 volts, I go below that 10, that I'm going to start to get the dim, then I know that if I keep that wire run around 200 feet max, even if I get a 2-volt drop, I'm still at that minimum operating range. So for me, when I'm doing a quick rough design and someone needs to know, hey, where can I place transformers? I haven't really laid this out yet. I'll just place a transformer within 200 feet in any direction, make sure I'm getting those fixtures picked up on that transformer. Now you can always run longer. Like I said, we can do the math later and figure out maybe I can go 220, I can do 225, but a really good rule of thumb is around 200 feet. So to kind of show you how that works is if I've got 12 gauge wire and I'm using a total of 40 watts and I'm on the 12-volt tap, I know by doing Ohm's Law, I've got about 3.3 amp load. Then I'm going to have 100 feet of wire. Now, what I need to do the math, you can see, is I'm going to take my amp load times 100. I multiply it by 2. And the reason why I multiply it by 2 is because it's alternating current, so it's going both ways. And then I got to multiply it by the resistance per foot. Now, I know the resistance per foot on 12 gauge is 0.00162. Make all that math, it gives me roughly a 1-volt drop. So this is the calculator that I use for all my projects when I'm working on it. I have it in an Excel spreadsheet. This is just a PDF just for this presentation, but I have an Excel spreadsheet. If anyone on the call is interested, email me after this presentation. I'll be happy to share it with you. it's all formulated out. So when in the spreadsheet, when you say 12 gauge wire, it'll automatically load the resistance per foot. So if you take it to 14, it'll automatically change that. It'll automatically calculate your amp load. And then when you put your wire in, it'll tell you your voltage drop. And then it'll finish it out all the way through and calculate it out. So it's a good spreadsheet. It's available to you if you're interested. Like I said, email me at the end of the program here, and I'll make sure you get a copy of it. But as we mentioned before, the each wire has a maximum amp rating. Now you cannot necessarily go off of what the manufacturer states because again, National Electric Code says we can only use 80% of the wire. We can't max the wire to 100%. We can only use 80% of that. Now, before I move on, I kind of forgot to mention this. The reason why the NEC only allows us to take transformer to 80% and wire to 80% is because anything we turn on, anything that we start that's got electricity, 120 volts, has what's called inrush current. So it's a millisecond. You can maybe catch it on your voltmeter, but it is like instant. And what's happening is when we turn something on, we're getting that inrush of current real fast before it regulates back down to where it needs to be, and that's just kind of that buildup, kind of a buildup of pressure, if you will. So we need to have that freeboard in the wire and in the transformer to account for that inrush every time we turn the system on. And then again, we're going to kind of fluctuate as we go through. So we want to make sure we've got room for that fluctuation. So back to the wire. If you're looking at manufacturer amp rating, he's saying they say 25 amps. Depending on this may be different. And you heard me say over and over again that 16 amps is kind of where I want to be at. We call that a D rating. So taking that 80%, we're at 16 amps. Now, for those of you that are out there that are quick on the math, quickly understand that, wait a minute, 20% of 25 isn't 16, it's actually 20. Why are you so low? Brian did his math wrong again. The other side with the wire is you have to also account for the temperature of the air. Now, this becomes a series of contention even within different reps of what the D rating actually is for 12 gauge wire. As I mentioned before, I live in Arizona and we still stay in the triple digits in the evening. So I err on the side of caution and really only size my wire to about 16 amps because of the correction factor due to the temperature that I have to deal with. Now, for those of you where 100 degrees at night would be a national emergency, you can get yourself closer up to 18 amps on that wire. And then this is sweater weather here for us in Phoenix. You can even go up to that 20 amp rating to make sure that you're within there. So for me, like I said, because of most of the work I do is here in the desert, I will err on this side, but you actually kind of have a range in between that 16 and 20 amps on 12 gauge wire. And trust me, to get to 20 amps, it's a lot of LEDs to put on a 12 gauge wire. So again, if I'm going to go back and use Ohm's Law for where I'm at on the 16 gauge, you can see I can roughly put 192 watts on 12 gauge wire and stay at that 16 amps. So at that 4-watt LED, which is one of our most popular MR16s, that's quite a few LEDs that I can put on 12 gauge wire before I hit 192 watts. So let's talk about how a transformer works, because I also get a lot of confusion on what happens, inside of a transformer as we're running through it. So if you take a transformer, if you were to take one apart, you'd see a big solid copper core. And basically what it is, it's a winding of copper wire into a core similar to this. And then what we do is we take 120 volts at the top and we enter it right there at the very beginning of that core. Then what we're doing is we're actually using voltage drop to our advantage. So as this electricity is running through the core, it's dropping. The voltage is dropping and dropping and dropping. And then when it finally hits to our different taps, that's where we tap into that core, pull out the secondary wire and get our secondary taps, 15, 14, 12 and 13 volts. So what's great about this is the transformers are actually, in essence, pretty dumb. They're not power sources or power supplies. They're nothing more than just taking voltage drop and dropping it. So when the fact that I'm saying they're dumb, there's no electronics in there for this to regulate or change. It can only pump out what it's taking in. So if this is off by a little bit, then these will be off. And that power factor that goes through there is actually a power of 10, right? So you can see is this is where we're at. So if I'm coming through here and this is off, it's going to change that to a power factor of 10. So if I'm saying that, if I only had 100 volts at the outlet, what do you think would be on the 12 volt tap? So if it's power of a 10, I would only have 10 volts on the 12 volt tap. Now, the big thing that we go through here is primary power is not exactly 120 volts. You can go in there and I can go and check in my office here. It's usually 121, 118, 122. And it changes throughout the day. So if you think about it, is I plug it in the morning, I'm going to have a different voltage at the end. So if this is 122, I'm going to end up with 12.2 volts on the 12 volt tap. And a lot of people will call. We've gotten calls in the past saying, hey, there's something wrong with your transformer. I'm only getting 10 volts on the 12 volt tap. Hey, check your primary. You're probably only getting 100. And at that point, you got to call an electrician and figure out what's going on. I got to go ahead and fix what's on the primary side. So the transformer can only pump out what it's taking in. Now, in my years of doing this, I can only count a handful of times where the primary power wasn't where it needed to be. I had one situation where it was way high, so it was 100 and I think it was 140 volts, and they were on the high tap, and that's what I was telling you before. So when they were thinking they were only pumping, 14 volts on the 14 volt tap, they were actually pumping out 16 volts, and they ended up frying 35 LEDs because they were giving those LEDs 16 volts instead of 15 because they didn't check, their secondaries to make sure it was what it should have been before they plugged it in. And I've had more situations where the voltage was too low, and then we were having problems getting the lights to even come on. So again, it's very rare, but it is possible, and it's a good idea to check when you're out there as you go through. So as we talked about as we went through there. So to kind of keep going here, so we're going to talk about the different wiring methods, and these are the three that I'm going to speak of. These are the ones that are pretty much prevalent out in the industry, and the biggest one that's out there now is a daisy chain. And this is primarily how systems get designed and get installed is we place the fixtures, we hang the transformer, and then we go ahead and run the home run wire, connect them all the way up. Now, I got a lot of people that will defend this because, hey, Brian, it's LEDs. We don't have to worry about voltage drop anymore. So I can just go ahead and do it. And this is a quick way to handle it. And the problem with that is, yeah, we don't have to worry about voltage drop as much. But now what I'm doing is I'm actually taking two connections at every fixture and I'm burying those in the ground. And then at this point, a system like this is just like an irrigation system to the point to where, an irrigation system usually fails at the connections, right? Very rarely does a main line just break in the middle of the main line. It usually fails at an elbow, at a T, at a riser, at some sort of slip fitting that we had to put together to connect two pieces of main line together. Same thing happens with lighting is if this system's going to fail, it's going to fail at these different connection points. So now with a small 5-light system, I've got 10 opportunities for this to create a failure. And the big reason why is we're using substandard wire nuts. These things fly off the shelves of distribution, whether they're the red wire nuts, but they're always going to be kind of that twist-on type wire nut that isn't a waterproof. And so what's happening is that since there is no weather protection, we're burying these in the ground. It's electricity. They warm up. The heat draws in moisture, and then I start to corrode the wire because we're putting bare copper, basically in the ground. And if this isn't protected, this corrosion here, this oxidation will actually work its way all the way up the wire, up underneath the sheathing, all the way back to the transformer. And this will act as a clogged pipe. And then that's where we get these phone calls. Well, I don't know what's going on. This thing worked great for 2 years, and suddenly it's not working anymore. Well, that's because it's corroded and gets stiff, and it's not carrying as much electricity as it did on day one. The other problem with this is that these types of wire nuts, any type of twist-on wire nuts, aren't designed for multi-strand wire. What they're designed for is for that indoor use. So if we've got solid core copper wire that's in the wiring in your house, Well, these actually have threads on them, and what's happening is, copper's soft. As I twist this on solid copper wire, it's creating a thread on the end of that, so then I can't pull that off, or it's a lot more difficult to pull that off. Well, the threads in here, there's nothing to grab onto because of the multi-strand wire, so we're just twisting and twisting all this up and making a big ball at the end of it. And then that ball is where the heat kind of generates, and that's why a lot of times you'll see the tops of these things burn up, is because we've created that ball at the end. So what you want is a mechanical connection. So what we move to is the hub wiring method. Now all unique lighting fixtures have a 25-foot wire lead, and so what we're doing is we're pulling that 25-foot wire lead back to one location. I'm now taking 2, 4, 6, 8, 10 connections buried in the ground, and I've turned it into 3 connections that are going to go into a hub box. Now, the reason why it's 3 connections and not 2 is that now I have the ability to wire an inline fuse inside that hub. So that's what this picture is here. So here's my inline fuse. We'll talk about these mechanical connections on the next slide. But by having that fuse in the field, I'm not asking the transformer now to be my primary source of protection. And this is the biggest problem that's out in the field, is that a lot of people expect this transformer to feel any type of short or any type of problem that's out there and trip itself. And when actuality, it may not do that, because what's happening is most transformers that are out there will either have a 15 amp or a 25 amp breaker. So let's say that this transformers are unique lighting 300-watt transformer. It's got a 25 amp breaker, and I've got a 12 gauge wire that is running this system. And I told you that that 12 gauge wire has, an amp rating of 16 amps. So let's say that we're going to go all the way up to the 20 amp rating based off of the fact that we're in a cooler climate. Well, that 20 amps is still not quite reaching the 25 in this transformer. So if I have a short, that wire is going to end up burning right here, because the wire has a smaller amp rating than the transformer, that the wire will actually fail before the transformer can recognize that there's a problem out in the field. So that's why we want to put fuses on each of these wires. Now, the big philosophy that I like to do is I want to make sure that my fuse is sized to the load. So if there's only, say, 5 amps on these 5 lights, I want to make sure I put a 6 amp fuse in there. I don't want to put a 16 amp or 20 amp for the wire. I want to size it for the load. That way, if I've got a problem, I can catch it quickly versus waiting for the wire to heat up and tell me later down the road that there's a problem. So by having that, we're adding that a lot protection. Now this seems kind of, like a lot of work. I'm going to have a hub and run a wire back, and I'm only doing 5 lights. So now with LED, I can do what's called an IntelliHub system. So now we have an IntelliHub, which is a bigger hub than the satellite hub, and this kind of acts as your main panel. So now I can have 3 hubs pulled back to one hub, one IntelliHub, and that IntelliHub pulled back to the transformer. Now again, now I'm taking what would have been 40 connections, so 20 lights, down would have been 40 connections down to 12, and now I'm fuse protected at each one of those locations. What's nice about this is that if this light's not working, then I know there's a problem at that light. If this whole bank is out, then I know that there's a problem at that hub. If the system's out, then there's a problem either at the main hub or at the transformer. And again, I'm not asking the transformer to be the sole source of protection for this whole system. Now, again, I keep bringing this back, saying, hey, this is electricity. We need to still think of it as electricity. So picture the electricity in your house, right? I'm willing to bet that somewhere on the side of your house or the side of your garage, there's a big master panel from the street. And then you've got sub panels throughout the house. One might be in your master bathroom, one's in the laundry room, one's in the utility room. So imagine if you didn't have this set up in your house and you had a short. You'd have to go take a hammer and start pumping holes in your drywall to find out where that connection was shorting out. Same thing happens in low voltage lighting, right? If we've got a problem, guys are now digging holes in the landscape trying to figure out where it's at, or they're just going, forget this, it's too much work. They go back and rewire the whole system. By having it set up as a hub system and engineering it this way, you can now troubleshoot this in the field by looking at fuses without having to start digging into the landscape. Here's a picture of an IntelliHub put together, so you can see I've got my inline fuses. Here's the caps that go over the mechanical fittings, and then I've got everything nice and neat, clean, fits inside that box. And if I ever had to go back and check something or maintain it. I'm not digging in the dirt. These aren't going to be covered in dirt and muck and mud. That they're going to be clean and protected. Always easy to maintain. Always easy to check as we go through. And these are the connections that you get inside the hubs. So in the satellite hub, this is the mechanical connection. So you can see there's threads here, and then that black cap gets threaded on top of it. It's filled with silicone grease. So that cap there goes over the top. And then I've got screwdriver to where if I ever needed to add or take one away, I don't have to cut this system. I can simply just loosen that up, put one in. And this is what comes in the IntelliHub. So a little bit bigger lug because I've got more, I've got more hubs and wire lights connected to it. Same thing, it's an Allen key that I can undo to add or take away fixtures if I need to. This is a little bit more sophisticated. This is a crimp, comes with a special tool. This is separate outside the hub, but we use these for more of the second story or downlight situations for more permanent. This you do have to cut if you ever needed to add or take something away. But again, it comes with the crimp tool. Now, what's nice about this is as we go through, where this doesn't add cost to the system. If you think about a contractor who's using really, really good DBY connectors and still burying them in the ground, he's still spending about $2 a pop, so $4 a fixture to use those DBY connectors. Where by the time you're done with this, it comes with everything. It comes with the fuse, it comes with the connectors, comes with the inline fuse holder. Really, all anyone needs to install this is a screwdriver and a pair of wire strippers. Um, and the cost of this will basically be the same as good DBY connectors all the way through. And finally, to kind of wrap it up, is here at Unique Lighting that we know a lot of designers and a lot of design build contractors. You don't really get the opportunity to lay out a system, right? You're trying to do it in the field, or if anything, you're laying out the fixture locations and not so much doing the wiring. So we offer a complimentary design service here at Unique Lighting where we will do as much or as little as you want. So we'll do all of the fixture locations, hub locations, wire design, even calculate the voltage drop and the transformer sizing for you. If you already know where you want your fixtures to be and where you want things to go, then send that over to us. We'll do all the wire design for you and calculate all this stuff out. So that way you know exactly where the hubs go, where everything's at. We do this in AutoCAD, so everything is going to be to scale. You're going to get a nice build sheet and everything that's out there, and everything's right to the point to where it is scalable, buildable. You can go out there and bid it, and it's great to you. Just because we do an AutoCAD doesn't mean we need AutoCAD drawings. We can do if you've got a PDF of the plan, we can draw on top of that. We can even do it from a Google Earth image. We do this quite a bit actually. So if you've got a system where, hey, I'm going to lay this out, we'll clean it up and we'll go ahead and lay that system out and do all the voltage calcs, or even if you're using a PDF or a CAD drawing, we can lay all this out for you. We make this look very similar to an irrigation plan, and we do that by design because more people have done irrigation installs than they have lighting installs. So that way, your newest guy on your newest crew, if he knows how to do irrigation, he'll be able to understand how to install low voltage lighting as we go all the way through. And then when the project's done, we'll actually give you the voltage drop sheet. So that way, when things change out in the field, whether we've added lights or taken lights away, made changes as we're installing, you'll get this calculation sheet that you'll be able to see what your actual wattage is. And then as I'm adjusting this, can I adjust, the size of my transformer accordingly? A lot of people kind of don't understand. They just, oh yeah, well, I'm putting in a 500-watt transformer. I don't know if I'm overloading it or not. Can we add 3 more? Yeah, I guess we can. This will give you the ability to have that informed decision that, yeah, you know what, you want to add 3 more lights. It's only going to be about 16 more watts on there. Yep, no problem. Go ahead and add those. We've got plenty of room. Or we're going to take 100 watts away. Yeah, we can go ahead and drop that transformer. So this is also part of that program. Again, it's 100% complimentary. It will be all Unique Lighting, so we can't do it with anybody else's product. Um, but it's no charge. There's no obligation. It takes about 1 week to produce a set of plans for you, and we're happy to help. So that is the end of my spiel. I'm happy that I've left 10 minutes on this one for questions. So we're going to go ahead and hang out here for a few minutes. And if you have any questions, please go ahead and type them in the box there, and we'll go ahead and answer them. And again, if anyone wants a copy of this at the end, um, please email me, and I'll send you a link to the video, or the copy of the recording, I should say. Like I said, we're going to hang out here. I want to thank everyone for taking the time and joining us today. And um, it's it's been fun doing these webinars. So, please hit me with any questions. I know sometimes it takes time to get them typed in. So we're going to hang out here for another 5 or 6 minutes, and we'll answer any questions that come up. Okay, I'm not really seeing any questions yet, so let you know that we're still here. Well, again, if you think of anything after we hang up, my email's there on the screen. Feel free to email me straight away, and I'll be happy to answer your questions via email, or give me a call. We can chat about it. I'm here to help. Okay, I see a bunch of people jumping off. So I haven't seen any questions, so I'm going to go ahead and call it here. Like I said, if you think of anything after the fact, please don't hesitate to email me, and we'll be happy to help. So once again, I want to thank everyone who stayed on and joined us today, and we'll talk to you soon.